All right, guys. So let's share our screen. We're talking about the solid. We have been talking about the liquids in so long. So crystalline, highly regular arrangement of the component you will find in the solid. There can be two types of solid. We call them amorphous versus crystalline, and the differences between the arrangement. Okay, so diamonds are crystalline, glass is amorphous. Both have different values, right? So see how repetitive sequence and how well arranged it is in crystalline state. So intermolecular forces play their role in what kind of structure, crystalline structure are going to be formed. Okay, in solids. So types of solid, there are definitely different types of solid. We have ionic compound, we have molecular compound. So we have examples for these two. We can always pick that up. Their properties are different when you talk about the molecular compound versus an salt review from General Chemistry 1. But we know that strong ionic interactions play their role in keeping the sodium and chloride, let's say, together. Whereas in molecular, we know that there's dispersion forces, dipole, these intermolecular forces playing their role. So there are things which utilize the covalent bond. We call the covalent network of the bond is about the elements. Okay. And if you look at the diamond graphite and silicon dioxide, it's also where you see the covalent bonding, high melting points are up. So for them, we see the metallic one, metallic bonds. We have a rod of iron. Where how come this all these irons are connected with each other? Is there some interaction playing its role? Yes, the metallic bonds are the ones playing their role in keeping all the iron in the rod of iron to be together, or in a piece of copper wire. These are all copper. Why? How come they are all together? Are they interacting with each other? Some sort of interaction is there. Yes, metallic bonds are there. So molecular solids held together by intermolecular forces, ice, dry ice, low melting point. They have low melting points. Ionic compounds have higher boiling point, greater than 400 degrees Celsius. Must know that. This is the packing of the water molecules, and that gives the beautiful arrangement of the water molecules because of the network of the hydrogen bonds that you see here. That the blue dotted lines is all the hydrogen bond being formed in a sample of water. Covalent network solids. Okay, so these are the things that we are supposed to discuss briefly, that the covalent bonds are formed in the diamond, graphite, semiconductors that you talk about, weak bonding between the layers of this compound that you see in graphite versus the down. So ionic solids that we are talking about, electrostatic interactions, attractions, I have already talked about that positive and negative ions are there and they have strong interactions between each other. That's why they have high melting points as well. We're talking about the elements, metallic network. You see that this is, let's say, copper 2 plus, copper 2 plus, copper 2 plus. The electron cloud around them has some sort of interaction that keeps them together. And that's that we call C of valence electrons. It holds atoms together because these electrons are being interacted by this proton here, and then the electrons from this one are being attracted. So this is how all they are connected with each other. They have variable melting point, they are conductor but are insoluble in water. So lattice structure in crystalline solid is the point of interest, and for that we look at the unit cell. It's the smallest repeating unit, which is called unit cell. So there are different types of unit cell we have to identify. Okay, so ionic sodium chloride, molecular water, atomic diamond carbon, they all have different types of units and then different type of structures. So one type of unit cell is simple cubic unit cell. We'll see how they are different from each other. Another one is called body-centered cubic unit cell, and then face-centered cubic unit cell. And this is like a natural thing where the solids are going to solidify in this crystalline form in the unit cell, which is the repeating unit in the crystalline structure. So what is unit cell? In general, a unit cell is defined by the lengths of the three axes A, B, C, and the three angles alpha, beta, and gamma. So this, if you see that there are three different axes A, B, and C, and three different angles, their value corresponds to the different types of unit cells. So if 90 degree, 90 degree, 90 degree angle for all beta and gamma you have, it's going to be the and all the lines C, B, and A, okay, axes are equal, then it's going to be this cubic type. Okay, so here is the list. This is what you're going to cover in the list. We have unit cells uh, of different type within the same type. Okay, so if we have cubic unit cell, we have three different forms of cubic unit cell. You're going to form the boundary of the unit cell is going to be a cube in them. But in that category of cubic unit cell, you have different types, which is simple cubic unit cell. We have face-centered cubic unit cell, and we have body-centered cubic unit cell. So the first portion that we are looking at here, and as I told you that the angles and the lines are all going to be equal to each other. That's how it's going to make the cube. How come they are different with each other is the number of atoms they're going to carry in each of them. Okay, so if you try to calculate the number of atoms present in each, like simple cubic unit cell, body-centered cubic unit cell, or the face-centered cubic unit cell, that makes difference. Okay, so do calculate, look at this, like only the so this is an atom here, this is an atom, this is an atom, atom. So each atom is contributing a quarter of itself inside the unit cell here. That's what we look at. What is inside the unit cell is what will be counted. So when you count all of them together, there's going to be one atom in the simple cubic unit cell. Altogether, there's pieces of all the atoms here that you see. Only the quarter of each of them is inside the unit cell, so that will be counted inside the unit cell. And you count all of them together, it's going to give you one atom, a sphere. That sphere is going to be one atom. Okay, great. Total, you see here are 8 of them. 1, 2, 3, 4, 5, 6, making a cube here, right? And the contribution from each atom is going to give you how much in each of it. Okay, so that's going to be just one atom here.